Today is the last talk given by Professor Chen Gang. He gave us about the spin-on Fermi surface U1 spin liquid in YbMgGaO material.
对，这个把那个 ，Thank you. Yeah. So let's continue. So when it's converted into PDF, so this notes was included, unfortunately. Yeah. So this is a recent progress on spin-off coupled spin liquid candidate, ytterbium magnesium gallium arsenide. So yeah. So I never gave this comprehensive talk on this topic. So today I probably have some more time to explain things in great detail, try to motivate the proposal why this thing is spin liquid, why this thing is spin-off Fermi surface. Sorry?
You change the title.
It doesn't matter.
Okay.
It doesn't matter. It's the same type of title. So so the thing is let's go from the very old theories of by not really theory, a proposal, a suggestion by Philip Anderson in the 1970s. So when he was if you read his paper, this is 1973 paper. If you read the paper carefully, he actually was motivated from this wave function for benzene molecule. So we learned in high school chemistry. So for benzene molecule, we need to use this rather than use this to refer this is organic chemistry, to refer the chemical form for benzene molecule, right? The reason why we use this is because the wave function is a linear superposition of so the electron wave function is a linear superposition of this thing and this thing. So the double link, the double bond, means the electron is preferred to sitting on these bonds rather than this bond. So it's a linear superposition of these two. As a result, all these sides are equivalent. It has 6-fold rotational symmetry. So this thing is used to label the wave function for benzene molecule. So this actually was proposed by Pauline. It's an RVB state, resonance valence bond state for benzene molecule. Yeah. So he, Philip Anderson was trying to motivate. It was inspired by this, I think, and proposed this idea to. Well, he was originally trying to think about some metal. Some metal maybe some electrons in metal may form this kind of state where the electron in the metal are shared by many different sides in this fashion. So later on, he was thinking about spin interactions on a frustrated lattice, like a triangle lattice. This is a triangle lattice. If you connect all these sides, that's a triangle lattice. So this black bond means the spin form spin singlet of this kind, up and down, minus down up. So this is a spin singlet. So this is one part of one possible wave function, or spin singlet covering on a frustrated triangle lattice, right? Anderson was thinking maybe if the system is frustrated, like imagine you put a Heisenberg interaction on this triangle lattice. At that time, around the 1970s, people don't know the actual ground state. People don't know the actual ground state for this triangle lattice Heisenberg model. Although nowadays we know it's a 120-degree state, but at that time people don't know. It's not a null state. So he proposed the wave function may be a linear superposition, a linear quantum mechanical superposition of many of these spin singlet coverings on the triangle lattice. So this is just one type of covering. You can arrange your spin singlet arbitrarily. So the ground state wave function is a linear superposition of them. So one of these and many others together, they form a total wave function. So in other words, these spin singlets they are fluctuating on the lattice. They fluctuate quantum mechanically on the lattice. So apparently this kind of state, does not break time reversal, and also doesn't break translation. So that's a great idea around that time, and people forgot that in the 70s until 1980s, when 1986, when the high temperature signal activity, cuprate high temperature signal activity was discovered, in 1986, right? So Anderson immediately point out the theory, the mother state for this cuprate is a motor insulator, because he think the cuprate can be thought of as a doped motor insulator. So he suggests the mother state, or the physical origin for this emergence of high temperature signal activity is so-called spin liquid, is a YbB spin liquid. So the resonant valence bond spin liquid. So on a square lattice, if you have competing interactions between the spin, you can arrange the spin into this fashion, and then you dope the spin, dope the electron into the system. So electron will experience spin charge separation, and the charge ions will condense and form a semiconductor. So that's a great, really, really remarkable, beautiful idea behind the high TC. It's an idea. So whether the YbB or other spin liquids is relevant or not for high TCs, it's not very clear right now. Still a lot of debates. So, but the physics of spin liquid is remarkably interesting. So, around that time, in the beginning of 1980s, there was a great discovery of fraction quantum Hall effect, right? That was real. So fraction quantum Hall effect was is arguably the only existing topological order that was discovered by human beings in nature, right? So it turns out fraction quantum Hall effect and quantum spin liquids belong to the same type of phase. Right? They both are exotic phases with fractionalization and emergent gauge structure. So the fraction quantum Hall effect is described by Chen-Simon gauge theory, while quantum spin liquids are described by various other gauge theories. So, and support the fractionalization. So these both quantum spin liquid and the fraction quantum Hall effect are not traditional Landau symmetry breaking state. You can see in the 1980s, these two different streams of theoretical condensed matter physics, high TC and the fraction quantum Hall effect, they merge together. So the underlying theoretical framework looks quite similar. So that's, if you are excited about theoretical physics, this is really remarkable. People started completely different things and find the underlying structure has a greater similarity, right? Yeah. So these are not Landau symmetry breaking states. So this brings up all the fundamental question, like how do we categorize the phase of matter, right? So this is one of the most if people regard this as a fundamental question, this is really a fundamental question. How do we categorize a phase of matter? Or does spin liquid really exist? So how do we categorize phase of matter? So leave Landau told us, if you study the symmetry and the symmetry breaking of the phase of matter, you can understand the phase of matter from the symmetry and the symmetry breaking. Yeah. So if you look at a liquid gas solid transition, so liquid and gas, they have the same symmetry. So liquid and gas are actually the same phase. So you can go from one to the other without crossing the boundary, right? Yeah. So but liquid and solid are different phases. So liquid are translation invariant by arbitrary translation, but solids are translation invariant only by lattice constant. So apparently liquid has a higher symmetry than solids. So the liquid and gas are completely different phases. You cannot go from one to the other without crossing the phase boundary, right? But for liquid and gas, there's same symmetry. But before Landau's symmetry breaking theory, we don't really know. We thought liquid and gas are different, but it turns out they're the same. You can go from one to the other without crossing boundary. Although in the phase diagram, you can have the region that the liquid goes to the gas cross the phase boundary, but that's not important. You can also go around each other. So the association with the phase of matter with the symmetry and the symmetry breaking is really is a remarkable idea, in the theoretical physics, right? So now it turns to this next. We are going beyond the Landau symmetry breaking theory. How do we understand and categorize the phase of matter beyond the Landau? Yeah. So this so much, this is sort of the introduction, how these two different streams of fields, topics in the theoretical condensed matter physics, they converge together. So the underlying structure beneath these ideas are the same or similar. Does people have any questions? Yeah. Yeah, so this is one slide introduction to quantum spin liquid. Yeah, so the existence of quantum spin liquid, at least in theory, is very well established. Yeah, so there's no doubt about that. So this thing really exists in, if you can write on a model, a somewhat realistic model, to show the system has a spin liquid ground state. If one like an exact solvable model and try to understand things from the exact solvable model, the Kitab model is a great example, and its variance. You can construct the Kitab model, a Kitab-like model on various lattices and find the exact solution. The exact solution supports the quantum spin liquid ground state, right? On a more abstract side, people carry out a mathematical classification of quantum spin liquids. This is initiated by Xiaogang Wen from MIT. Yeah, he invoked many of these ideas of classifications and sparked the interest in the theoretical community. So in addition, there are numerical studies working on the models that are not exactly solvable but understandable from more theoretical suggestions, and numerically can confirm these things do seem to support quantum spin liquid phase, right? So quantum spin liquids, or sometimes people call it a spin liquid, is a new phase of matter. It's a completely new phase of matter.
I have a question. So in all of these claimed spin liquids, do they really exhaust all possible all possible local orders and what you could claim, or just maybe they say, oh, there's no near order, there's no ideal order?
No, you can measure direct consequence, not measuring, not just measuring in the absence of order. No.
For the numerical result, there are no so strong evidence for the function of the topological internal entropy. There's no really conclusive concept.
Yeah, that's a great question. Yeah, so
theoretically, practically solvable, that I think that's true. But for the numerical evidence,
you mean theoretically they can really exclude all possible local orders?
But you can construct it's possible to construct a model. You know that is no order.
Oh, okay. You have one possible. Okay.
Yeah. So yeah, to answer this question, so numerically is like in some sense is like an experiment. So theoretically, we can suggest some key sharp observables to confirm the existence of quantum spin liquid for certain experiment or for certain models, right? Then you can ask experimentalists or numerical people to test whether this phenomena can be observed or not, right? So one of the key things is there is a fractionalization, there is an emergent gauge structure, right? So you can see this fractionalization by finding the continuum, and the continuum may have a certain particular structure. And this structure, if the structure that is observed in experimental theory and the numerics consistent with theoretical prediction, that gives you some strong evidence that spin liquid is realized. So we can go beyond this topological entanglement entropy. So many quantum spin liquids are not topological spin liquids. So they don't have a topological entanglement entropy. Yeah. Yeah. So really important thing is to me is that the experiment and the connection between the bridge between experiment and theory, right? Not constructing some model like complicated looking Hamiltonian. The really important question is find the experimental candidate and try to understand these experimental candidate. What's the actual nature of this candidate ground state for these candidate materials? People propose many of these spin liquid candidates over here, and yeah, I don't want. Well, so I studied most of them, but I don't have time to get into all these details one by one. Yeah, so yeah, each of them require different modeling and different understanding and have different phenomenology. Yeah, so we need to combine, microscopic understanding, microscopic modeling with various complex experimental phenomena together to judge, whether quantum spin liquid or any other, physics is relevant for this kind of system. Yeah, I want to point out that some of these candidate materials has been ruled out. These are probably not quantum spin liquid, but the physics can be very interesting. They don't have to be quantum spin liquid. The physics itself, is interesting on its own. We don't need to be obsessed, with a quantum spin liquid, right? So I take this view, everything existing in nature is interesting on itself. So we don't need to obsess these things, attach everything to quantum spin liquid and then other things up there, right? Yeah. So this is now I go back to the central part of this talk. So I will talk about this YbMgGaO material, this triangle lattice rare earth magnet. So this is this is the outline. So first I give the early thermodynamics and the microscopic modeling. So the later on provide a phenomenological approach and the neutron scattering result, and some prediction of weak field regime and some other sort. Yeah. So let's go to the simplest experiment, like the early thermodynamics and the microscopic modeling. So yeah. Yeah, so this material was found in Qiming Zhang's group. So I mentioned it to you. It's a triangle that is with ytterbium ion. Ytterbium has 13 electrons. So there is the great theorem in condensed matter physics. It was initiated in one dimension by Lipschutz-Matters in the 70s, 60s, 70s. So it's called LSM theorem. So Lipschutz-Matters theorem. So it says, this theorem says that in one dimension, if we have odd number electron per cell, the system has to be gapless. If we want to have a gapless state, the system has to break translation symmetry such that the unit cell have even number of electrons. Right? Yeah. So in 1D, we know like gapless state is a gapless 1D, with all the electron filling. That's a Luttinger liquid. Right? So this theorem has an extension to high dimension first made by Oshikawa in around 2000, and Matt Hestin. He's now in Santa Barbara, the Q stage in Santa Barbara. He further provide some proof for general dimension, 2D and 3D. Excuse me. Yeah. So this is a remarkable theorem. So in high dimension, they managed to claim that for a motor insulator with a global U1 symmetry, so they require global U1 symmetry. So if the system has all electron filling, all number of electrons per unit cell, the ground state has to be, gapless or topological. So this is a very strong statement. This seems to be quite useful. If you look at the number of electrons per cell, if there is no spontaneous symmetry breaking, so the ground state has to be exotic or topological or gapless. So, but the theorem assumes a global U1 symmetry. A global U1 symmetry is not often present in a physical system. Especially in the system with spin-orbit coupling, that applies to this material. So the global U1 symmetry is completely absent in this system. There's only lattice symmetry. So this theorem, although it sounds very powerful, doesn't work for the realistic spin-orbit coupled matter. Right? So these people. So Watanabe now is a assistant professor at University of Tokyo. Paul is a postdoc. Will be a postdoc at MIT. Wishman is a faculty at Harvard. Mike Zalato is a faculty at Berkeley. So they came and proposed this extension of the theorem to spin-orbit coupled matter. So they argue as long as time also symmetry is preserved. It's a very strong statement. They use entanglement argument. As long as time also symmetry is preserved, as long as the system has all the electrons per cell, for spin-orbit coupled motor insulator, the ground state has to be exotic. So this is a strong statement, very strong statement, for like a motor insulator with all the electron filling. If time also symmetry is preserved, right? So time also symmetry is Ising symmetry. In 2 + 1 dimension, or in 2 dimension. So this is discrete Ising symmetry. If it is broken, it has to be broken at finite temperature, right? So in 1 dimension, it does not have to be at finite temperature. In 2 dimension, there must be a finite temperature phase transition if time relative symmetry is broken. So that means if you do, any kind of measurement, you will see a finite temperature phase transition. You will see a TC, critical phase transition. But the thing is, the time relative symmetry breaking or any signature phase transition is not preserved in this material. So that means the time relative symmetry is preserved down to very, very low temperature. So then you can apply this extension, this recent extension that. So since time relative symmetry is preserved, so the ground state of this material has to be exotic. So this is the underlying theoretical logic. So the system has to be exotic just by observing the thermodynamic measurement. We can make such a claim, right? So that's what we propose. This is likely to be together with Qiming Zhang and other people. So we propose that. This is the first strong spin-orbit coupled quantum spin liquid with all the electron filling and effective spin 1/2. So this is also a first clear observation of this behavior.
That's all. So the heat capacity is for electron, right? It's the electronic heat capacity.
It's the spin heat capacity.
How can you measure spin heat capacity?
Well, it's a spin heat capacity. It just measures.
It's only phonon and electron in real experiment.
Yeah, it's just electron and electron. The charge is frozen, so the remaining one is spin. Yeah.
But in this sense, then the corresponding heat, the specific heat coefficient will be divergent.
Yeah, it is divergent.
Then in the actual picture, something becomes very heavy, right?
No, it is divergent. Yeah. So the density of states diverge. Yeah.
Yeah. Then does that mean like if you observe a certain excitation or something like that, it may be like a flat, almost flat?
No, it's not like that. The story is not like what you said. So So I need to invoke this. Yeah. Okay, turn to this whiteboard. Yeah. So the story is there is a spin-on Fermi surface with a momentum kf. This is the Fermi momentum kf. So this is a completely filled with spin-ons. So the low energy degree of freedom or low energy excitation are spin-on particle holes, right? So, but these are coupled with the U1 emergent U1 gauge fields. You know, this is a strong coupling theory. So the coupling, this coupling is not weak. It's order of 1. It's not like quantum electrodynamics. This coupling is small due to the very weak, fine structure constant. The fine structure constant is very small. You can do perturbability expansion. This is not, right? This is not. So when this light or when this emergent gauge field is propagating, so it will create a particle excitations of the spin-ons, right? And also this diamagnetic bubble. So this is the diamagnetic bubble. This is the particle excitation. So this is what together will renormalize. We generate a self-energy for these gauge field bosons. So this will create overdamped effect for the propagation of these gauge photons. So this is overdamped.
Yeah, but at a phenomenological level, if specific coefficient divergent, and in your picture it looks like the spin-on Fermi, and I don't know its terminology, right? This kind of quasi-particle becomes infinitely heavy. How can it propagate?
No, let me finish. Let me finish. So the renormalized photon propagator further renormalize the self-energy for the fermionic spin-ons. So the self-energy of the fermionic spin-ons is scaled like omega 2/3 in a crude RPA couple calculation. So this is the RPA theory. Many later more involved theory like double expansion and codimensional regularization also give you similar result. So this dominates over the in your self-energy in your spin-on propagator. There is the denominator is I omega, minus. So the G omega would be I omega minus CF K. So now have a self-energy correction. So this self-energy correction will dominate over I omega. So that will give you a divergent density of states from the power accounting. So that will give you a T 2/3 result in your heat capacity. So that's the reason. Yeah, you get divergent density of states because of this renormalization of fermion self-energy by the renormalized gauge photon. It is massless. Massless.
Yeah, that's the one actually very inconsistent. So it's massless and it becomes infinitely heavy. So there's something maybe RPA has some issue here actually.
There are some issues, yeah.
The RPA really is not a stable measure.
Yeah, let's just continue. So yeah, so this is very, very low energy physics. Let's just ask the question. I mean, the most important question is not just this low energy physics. The important question is whether there is a fractionalization going on here. So the inelastic neutron scattering measurement is consistent with the spin-on Fermi surface result. So I think this is a spin-on Fermi surface U1 quantum spin liquid.
And there's a problem. There's a question raised by Xiaogang. He would want me to ask you the question. So he said in his sense, spin-on in conventional sense should be trapped. should be traveled somewhere. I mean, the quasi particle, you know, the spinor discussed here is different from the spinor discussed in the beta answer community. That's an exact representation there. And here, just quasi particle terminology. So, from his understanding, the spinor here should be traveled somewhere, and there's with a gap which can protect spinor. He just can't understand. He cannot understand why. At this situation, at gap situation, spinor can still be protected by somewhere, like thermal fluctuation or interaction or anything. How can such a stable quasi-particle can still survive here?
Well, I don't.
So.
I don't understand the question here. Is it the original?
Yeah, that's the original one. Yeah. He's in his understanding, like a spinor. For his understanding, the spinor there should have a certain charge, right? And then the spinor can only carry spin there, and there's no charge degree freedom. And at this situation, he thinks there's a well-defined quasi-particle here, and the spinor here has a gap which you can protect it. But now, at least at your situation, he thinks that there's not such a gap to protect that. Then there's not such a stable spinor. There should not exist such a spinor forming surface. So he just wants to know what's your physical explanation on this.
No, so this is I think what Xiaogang was talking is more like in a topological spin liquid that you have gapped the spinor excitation, like in a Z2 topological you have E particle that's fully gapped. You can even define Brownian statistics for these gapped excitations because you can define adiabatic adiabaticity for this gapped system. But for a gapped system, you cannot do that, right? So our understanding for gapless quantum spin liquids is not so great, especially for the system with a large forming surface. With this, with a discrete number of gapless points, like Dirac spin liquids, where in the spectrum there is only discrete number of gapless points. So that over there, things are much more controlled. So you can do things. You can understand the low energy physics by doing a controlled expansion near these gapless points. But if the system has, such as this one, has infinite number of gapless points, and they are strongly coupled with this, emergent gauge bosons, so things become very, very complex. So the low energy physics is not very understood, even today.
Mm-hmm. I think even for the conventional surface, it's still very hard to do.
Yeah, even for these conventional field theories with forming surfaces is already very hard. The critical theory for the forming seas is not very understood. So there are people invent many expansions. So in the 1990s, so first pointed out by Joe Polchinski, who passed away, maybe last year. So he pointed out, the tangential boson is important because of energy momentum conservation. So the boson, the tangential coupling. So he then realized the patch theory. There is a patch theory, reduction of this theory into a patch theory. So then, Weilchek and Chetanayake in 1994, 95, they invented epsilon expansion. So they modify the dynamical property of this emergent gauge bosons, so that provide a so-called another epsilon expansion to the problem. So Sonsik later in around 2009, he pointed out the conventional RPA calculation. So the RPA calculation was first performed by Patrick Lee and Nagosa in 1992. So so Sonsik pointed out that this Lagrange calculation has a problem. So the certain factor diagram, actually that was ignored in the Lagrange calculation. Lagrange just gives you a recipe to organize the Feynman diagrams. So certain Feynman diagrams become more important. Certain Feynman diagrams become less important. So in a Lagrange calculation, so Lagrange just gives you a recipe to organize, to select which Feynman diagram is more important. But a priori, this Lagrange calculation doesn't mean it's going to be important. It's not fully justified, because there are only like one flavor or two flavors of these fermions.
And how can I use RPA to justify Lagrange? RPA itself is also unstable. It's uncontrolled.
It's not justified. No, I'm not. Nothing is justified here. So so something point out that there is a flaw in this calculation. So then the way of organizing the Feynman diagram is not the traditional way of organizing Feynman diagram is not probably not right. So he proposed another way of organizing it. It's called genus expansion. It's providing the topology based on the topology of the first diagram to give you a guidance how you make the expansion. So then, well, it's a suggestion. He didn't really perform the calculation. So it was a great observation. He noticed in the connection between this way of organizing the first diagram with the matrix theory in this quantum field theory. It's a matrix field theory. So later on, this MIT group, sent to Liu Hong and his student. So they figure out they combine the Lagrange expansion and the epsilon expansion. So the epsilon expansion invented by Wilczek and Chetanyak, they combine these. They call it the double expansion. They make sure they keep n to be small, n to be large, epsilon to be small, but use 1/n times epsilon as the expansion parameter. So if the physical system is located in a regime where double expansion works, then it will be good. So that was actually a very nice piece of work. Yeah. So around the same time, Max Matesky at Harvard and his supervisor, Sachdev, they actually performed the high order expansion. Lagrange doesn't work, but then they said, we just doing Lagrange, going to high orders. They find that this self-energy correction, has a momentum dependence. So it not just has a energy dependence, there is a momentum dependence. So they found that that was a heavy calculation. Yeah. So some.
No, actually, I think their Lagrange calculation is really bad actually compared with the real experiment.
This is recorded. Remember.
You mean you said that the heavy calculation is that a three-group level calculation? To which order do they go?
They go to high orders. Yeah, I don't know. You can examine the paper. Yeah, they have two papers. So I want to say that later on, Sonsiger was not satisfied with this double expansion. He invented another expansion called the codimensional regularization and dimensional regularization. Try to extend the idea what we used in 5-4 theory. So in this quantum statistical mechanics, we actually have this in this how we obtain this Wilson-Fisher fixed point. We're doing a codimensional regularization. We going from the 4 dimension to be 4 minus epsilon expansion. We're doing expansion in terms of epsilon. So, but for this codimensional regularization, he buried this Fermi surface, which is a Fermi line, in 2 dimensions, buried this in a higher dimension. So in 2 dimensions, the codimension of a Fermi surface is 1. Codimension means the dimension not being occupied by Fermi surface. So this is the actual dimension here. So if you bury this Fermi line in 3D, the codimension is 2. You can bury this in higher dimension. So he used this codimension as the expansion parameter. He found the critical dimension is 5/2. So he carried out the epsilon expansion and found the RPA result seemed to work. But this codimensional regularization, it radically changed the problem. So that can be an issue. It radically changed the problem. So it may not be right. It's different from this 5-4 theory that we know that theory is scaling invariant. So we are justified to use this.
No. That's not scaling invariant.
No.
No, when it's only scaling invariant when the total dimension is below 3. If it's 4, 3 plus 1 is not scaling invariant because they are logarithmically behaving inside. There's no way to be scaling invariant. Yeah. So it's not analytical, right? It's not analytical, then you cannot say scaling invariant or not, actually.
We can talk about this later.
I'm working on this model for 10 years, so.
Yeah, somehow my training, my understanding of things is a little bit different from.
We need to go beyond one loop. We need to go beyond. When you reach two loop, everything will be clear. Yeah. You cannot talk about in one loop. At one loop, everything is clear. It's scaling invariant. Everything feels like that.
This is recorded. If one makes some mistake, there will be.
No, there's no mistake. I worked in this model for 10 years. How can I make mistake?
Yeah. So the thing is, so this theory, the critical Fermi surface coupled to critical boson, this critical boson not necessary to be a gauge boson. It can be other. So this theory is other effective field theory. This describes not only this emergent, Fermi surface coupled to emergent gauge bosons. It can also describe the real Fermi surface have a magnetic order or some kind of isomagnetic order, some kind of nematic order. So this kind of order, this is strongly fluctuating order coupled to the critical fermions on the Fermi surface. So this applies to, for instance, as people suggest, to iron-based semiconductors, to the cuprate semiconductors, to the 1/2 field Landau levels, fraction quantum Hall effect. So this is the field theory is a general. So but the field theory itself is not well understood yet, right? There is no controlled expansion to understand the low energy behavior of this field theory. And also, as I said, the theory is probably not really we don't really know it's really scaling invariant. So this dimensional regularization and codimensional regularization, theoretically, is very beautiful, seems to be powerful. Maybe, but it changes the problem. It changes the problem in a significant fashion. It's not obvious this dimensional and codimensional regularization is smoothly connected to the original problem. So it changes the problem. Yeah. So. Yeah, let's continue. So don't worry too much about this low energy physics. Just ask a question whether fractionalization. So the key thing is whether fractionalization occur in a spin liquid candidate. So yeah. So today I'm not going to worry about too much about time. Let's just explain things in a historical fashion. So the great thing is, so in the last 2 decades, our understanding of quantum spin liquids has been significantly improved. So when in the 1970s and 80s, when Anderson proposed this notion of quantum spin liquid, people really don't understand. What's behind? What's the right language to describe a quantum spin liquid? As Jenda was saying, just using this absence of order to describe quantum spin liquid is not sufficient. We need more descriptive understanding rather than more negative description, right? So then, I think in the 90s or around later. So people think maybe fractionalization, with a fractionalized quantum number, quantum number excitation with fractional quantum number would be a right definition or description for quantum spin liquid, for the physical property of quantum spin liquid. So this apparently happened in one dimension. So in one dimensional Heisenberg chain, so we know there are spin-on excitations. These one-dimensional spin-ons are actually a domain wall. It's like a domain wall. It carries spin 1/2. Yeah, so the spin 1 excitation is fractionalized into 2 spin 1/2, spin-on excitations in one dimension. But how do we extend these things in high dimension, right? So how do we support fractionalization in high dimension? So we know, like if you go to low energy or infinite energy, so we know one theory in theoretical physics called the gauge theory. That theory was appearing before the proposal of quantum spin liquid. People are just playing as a toy model, extend the continued gauge theory into discrete gauge theory. Even Professor C.N. Yang, he was generalizing this. His YbMgGaO theory is an abelian gauge theory. So in the physics community, people are interested in gauge theory. So apparently, gauge theory supports fractionalization. In other words, the connection is not that strong. So in gauge theory, there is a phase called deconfinement phase. So in deconfined phase, just like in QCD methods, quark are confined when you go to low energies, but at high energy, quark are fractionalized. You can separate them without costing too much energy. So the deconfinement is strongly tied to this fractionalization. So then the right theoretical language to describe a quantum spin liquid would be in terms of some kind of gauge theory. So the deconfined phase of a gauge theory would probably describe quantum spin liquid. Yeah. So let me focus on this specific case. This is a U1 quantum spin liquid in 2 dimensions. So in 2 dimensions, 2 plus 1 dimension in a U1 quantum spin liquid, or for U1 gauge theory, a pure U1 gauge theory. So we know, on a lattice, U1 gauge theory is compact, and Polyakov, this Russian theoretical physicist, pointed out due to space-time multiple event or space instanton event. So these monopoles, these instantons, they always proliferate and condense and lead to confinement. So in 2 plus 1 dimension, this compact U1 gauge theory always confining, and you obtain some confinement. So you don't get a fractionalization, you don't get a spin liquid. But if you have gapless matter, so that appears in the energy theory. So that will, enhance the scaling dimension for these multiple event. So they will suppress these multiple event. So the space-time multiple event will be suppressed by the presence of gapless matter. And it was argued that because Fermi surface they have lot of low energy density of states, have a lot of gapless matter on the Fermi surface. So then spin-off Fermi surface, U1 quantum spin liquid with spin-off Fermi surface can potentially be stabilized in that manner. So that's the reason why this spin-off Fermi surface U1 quantum spin liquid can potentially exist due to the presence of infinite gapless points of the spin-off matter.
What is here the charge particle to the gauge field? Is the spin-on itself or the particle spin-on from the surface?
Both of them, right?
Both of them.
Yeah. Well, in a lattice level, just it's a minimal coupling. On a lattice, the model is just a minimal coupling. If you go to low energy, it's just the spin-ons on the Fermi surface coupled to this dynamic U1 gauge field. Yeah. So, well, I talk too much about the background. Let's switch to the. So I fluctuate between chemistry, fundamental theorems, abstract field theory, and the gauge theory, and these chemistries. People are probably not used to this kind of style, but if you want to do things close to experiment, at the same time do not lose theoretical height, you probably need to have that kind of skill. Yeah. So the microscopics. So this thing is in a triangle lattice in a D3 point group. So the total moment is J equal to 7.5, and fraction on the crystal field it becomes these 4 doublets. Each of them is 2-fold degenerate. The 2-fold degeneracy is due to Kramer's theorem. So this is Kramer's degeneracy. Yeah. So this gap is pretty large. It's order of 400 Kelvin. So the ground state doublet can be labeled as effective spin 1/2. Yeah. So this is the effective spin 1/2. Yeah, my student and we carry out this modeling. It's a complex model. It's a Kramer's doublet, describing Kramer's doublet on a triangle lattice. This model is anisotropic both in the spin space and in the position space. So the interaction depends on the bond orientations. Yeah. So this thing, you can it's anisotropic in spin space and in position space. If you do polarized neutron scattering measurement, the correlation function for different spin component can be different due to this anisotropy. So people actually carry out polarized neutron scattering measurement and found so their data clearly support a model with the first neighbor and the strongly anisotropic exchange. So let's see. Yeah. So these dots are experimental results. These curves are theory, right? Seem to quite agree with experiment quite well. Yeah. So we first carry out very conservative, rather conservative. Yeah.
Can I ask a question about the relation between this model to your previous model you talked about yesterday, the Yang model?
Yeah.
And, in that case, one say doublet is like a non-primer degenerate state, and the feeling is even number of. And in this case, it's an odd number of primer degenerate. So this case it forms a spin on surface, and in that case there is completely filled. So you are considering some excitation, like magnon excitation. Basically, my question is common. Is that correct?
Well, yeah. So over there, I already consider ordering tendency. Yeah, this model here can also support ordering tendency. But the thing is whether there is a region in the phase diagram that supports the spin liquid. Yeah. Yeah. So there are lots of parameters in the model. So the phase diagram is large, right? It's large. So the question is whether there is a region in the phase diagram that supports the quantum spin liquid. Then some other region in the model supports ordering, right?
So you don't ask the question you asked yesterday, because in this
Yeah.
one state is primer
Yes,
generate,
yeah.
and it is hard to, because all three spins coupled to neutron scattering, and things get complicated. So you don't ask the same question you asked.
Yeah, that's true. That's a good comment. Yeah, yeah. So the question here we are going to address is completely different. Yeah. So the question guides the research, right? Yeah.
So how many parameters inside?
There are three independent parameters. Two of them, the first two can be determined by Curie-Weiss temperature measurement for single crystals.
I mean, JGG and J plus and J minus.
Yeah, so this can be determined by Curie-Weiss temperature measurement.
So these three parameters.
So you can fix two of them and vary the other two. So two of them are fixed by single crystal Curie-Weiss temperature measurement. So
for the gamma thing, it also has the two parameters because the gamma is number.
well, if you expand in terms of xx, sy, so there's no complex parameter. These are all, yeah. So this is some mean-field semi-classical calculation Yao Dong and I did. It's all published. This is all PRB published. I didn't update this, but yeah, you can see. So because of this approach, the approach we are doing is semi-classical plus some quantum fluctuation. This is a conservative approach, as I said. This is not trying to tell you we are finding quantum spin liquid in this phase diagram. This is just tell you in this phase diagram we found the various orders, and we ask how robust is this order against the quantum fluctuation. This is rather conservative. So if the quantum fluctuation in this ordering region is very strong and melts the order, so that means in this region we may potentially find the quantum spin liquid, right? So this doesn't really solve the problem. This just tell you maybe this model captures the physics of quantum spin liquid, the microscopic mechanism to have quantum spin liquid in this model. So this is the this is the thought behind. Yeah, it turns out it's true. Like in this white region. So
So you draw the few different orders here. So based on which order you plot this Gestapo?
No, these are 3 different phases, are 3 different orders.
Oh, 3 different orders.
It's all drawn here. So region 1, 2, 3 are different phases. They have different order. So
between the phase boundaries, the continuous phase transition. Or
it's 4th order. It's 4th order. So the yeah.
What's the right figure? The right figure.
I'm expanding. So this right figure tells you on top of these ordering phases, if you consider quantum fluctuations, the quantum fluctuation melts the order in this white region. So this color means the value of quantum fluctuation. So if the fluctuation is large, exceeds the value of the spin, exceeds the value of order, so this order will be melted completely. So this white region is where this quantum spin liquid melts. Yeah. Oh, sorry, the magnetic order melts. Quantum 0 point fluctuation. Quantum fluctuation just tells you how strong the quantum fluctuation melts the magnetic order. It is a linear spin wave theory. This is not linear. This goes beyond the linear spin wave theory. This is spin wave theory. You have order. You look at what's the fluctuation around this order, and if the order is strong, it kills the order, right? So this is a rather conservative approach. It just tells you maybe the model supports the quantum spin liquid scenarios. So this region can potentially support the quantum spin liquid. Yeah. So the phenomenological approach. So these are microscopic approach, but very conservative. Yeah, very conservative approach. Yeah, this phase diagram is verified by DMRG. No, so I understand some DMRG, but not understand DMRG in great detail. I was told that DMRG may favor ordering, particularly because this model has no conservative quantity. So the model we wrote down has no conservative quantity. There's no conservative global U1 or magnetization is conserved. Nothing is conserved. So the way to use DMRG become complex. How many steps you keep, how many steps you use can be an issue. So the things there is a tendency towards ordering. Well, I don't know. I trust them because some of order is reproduced over there, right? This is 2D system.
You need to design some clever tensor networks.
Yeah, this is great numerical physicists that can figure out a way to solve the problem. Honestly, I don't understand these numerics very well. So I think they can be an interesting, it's a very interesting problem for test these numerical techniques, right? So for this model, which apparently have a sign problem for Monte Carlo, so only ED, exact diagonalization, which is only works for few systems like 20, 40 spin, maybe 40, 20. 20. This system doesn't have conservation laws, so maybe only 20 spin, order of 20 spin. Yeah, yes, no, apparently. This F electron are very short range. The only thing you need to worry is dipole interaction. But dipole interaction can be numerically estimated. No. Yeah, dipole interaction, as I said, it can be numerically estimated. You can compute that. Right? You know the moment, and you know the distance. So dipole interaction, here we only need to consider dipole interaction beyond the first neighbor, right? So beyond the first neighbor dipole interaction already included in this model. This is a generic model. It includes all possible microscopic origins. So the second neighbor dipole interaction you can estimate is much smaller than the parameter here. Yeah. Yeah, so I think there are some opportunity for the numerical physicists, numerical oriented physicists. One can try to figure out what's the best algorithm to study a model of this kind with a lot of anisotropy and no conservation laws, right? So ED maybe may not be so great, especially for gapless system. Monte Carlo does have a sign problem. Yeah, so DMRG maybe good. DMRG tensor network can be potentially powerful tools for solving a model of this kind. Yeah. So.
You are going to experiment, right? The next slide.
Yeah, I'm going to experiment. So. Yeah. So the. Yeah. So the. Yeah. So the continue. So this is the neutron diffraction pattern. There is a huge continuum. So in the momentum domain, there is a huge broad continuum. In the energy domain, there is also a huge continuum. It's a huge continuum. Yeah. So this continuum. So this work is collaboration with my colleague and his student, and also my grad student transferred to UC Santa Barbara. So this is consistent. This result also consistent with another neutron group from Martin Morgel from Georgia Tech. Yeah. So their paper is in Nature Physics. So the theoretical proposal is so we don't know how to solve the model numerically. DMRG did not tell us that's a spin-forming surface. Actually, the proposal of the spin-forming surface is much before the numerical result. Okay, these are all 2016, so much earlier. So the proposal, the phenomenological proposal, based on reading the experiment, is likely to be a spin-forming surface state, right? So this is the extended Brillouin zone. This honeycomb is the first Brillouin zone, and this blue one is the Fermi C. Is the Fermi C. Yeah, is the Fermi C, and in Fermi C, the spin-4 excitation would be a particle excitation. Just like a Fermi surface, the collective excitation would be particle excitation. So particle excitation across the Fermi C. So the particle excitation, any kind of particle excitation can happen right next to each other across the Fermi C, or here, or here, or here, or across the Fermi C by 2kF. So that means in the momentum space, if you fix the energy, there is a broad continuum of excitations in the Brillouin zone. So this is the continuum.
In the middle is the theoretical result. Actually,
yeah, this is a theory. This is experiment.
I see, but 7.5T is about at what energy? E is equal to 7.5T.
Well, I don't remember the energy, so it's kind of cut in the middle of the bandwidth. Yeah.
So it looks like the peak position, the resonant peak position, deviate from theoretical.
Yeah, that's a good question. That's a good question. Yeah. So
shoot a lot.
So this is a remarkably simple model. If you add other ingredients, you can fix it. You can redistribute the intensity. So this is a remarkably simple model.
But you have two parameters.
No. There's no parameter here.
Oh, no parameter.
There's no parameter. So this is nearest neighbor Hopkin Hamiltonian on a triangle lattice. There's no parameter. The Fermi surface is fixed.
Okay.
Right. So if you add parameters, you can do a lot of things. I'm just trying to use the simplest, no fine-tuning model. There's nothing is fine-tuning here. Ask the question whether we can reproduce the experiment in a qualitative or semi-quantitative way, right? So yeah, so it turns out so this is the spin-on bands, and this is the Fermi level. So this neutron scanner measures the particle excitation across the Fermi C. So this particle excitation can be here, or here, or here. So that explains why there is a broad continuum at low energies. Moreover, if you increase the energy, near the gamma point, there is the suppression of spectral intensity. Then the suppression of spectral intensity.
The comparison, like at the phase momentum, you cut along a certain momentum, and you plot out the DSF versus the energy.
Yeah, then it's
You see the resonant peak, and or maybe some peaks are there. That is another very important information.
yeah. So that works for intermediate to high energy. It works very well. For very low energies, this is mean field theory. For very low energy, it doesn't really work because this ignores all these, low energy gauge function is completely ignored. So, yeah. So at very low energies, the mean field theory is not going to be reliable. Yeah.
That's counterintuitive. Usually, mean field theory should work.
No.
Because I spin wave to compare the longitude distribution.
That's for spin wave theory. That doesn't. Yeah. So at the low energies, all these gauge fluctuations become very important. You get a divergent density of states. So that means you would get a higher intensity at the low energies. Yeah, you get an experiment supports this view. Experiment see intensity actually goes up at low energies. So this is consistent with the theoretical suggestion. So, but here, we only use mean field theory. So that's
Maybe a naive question. For this, the theoretical calculation is from the field, right?
Yeah.
What kind of from the signal can capture the significance?
Well, you can look at the spectral intensity. If you look at this spinel continuum, you can compute the dynamical spin structure factor that is directly measured by neutron scattering measurement.
But the theoretical is from the field.
Yeah, you can. It doesn't matter. Mean field can predict the spectrum, and the spectrum we produce is yeah. So this is the theory.
Do you have another way, like maybe?
So I guess the logic here is like you see some fermionic excitation, so you construct a model with free fermions, right?
This is a phenomenological description. The way to you asked me this, right? So the thing is the best the mean field theory is the way to provide the variational wave function for physical looking phenomenon.
So the relation between this one and the original model is because of the manipulation.
I guess.
So focused on the weak field regime, where the spin liquid is preserved and fractionalized spin-on remains to be a good description of the magnetic state. So the thing is, so we apply a weak magnetic field, weak such that the spin liquid state is not being destroyed. Right? So you do something little to the system and look at the response. If this is something little, if this response can be theoretically predicted as a consequence of the fractionalization, and this prediction is being confirmed by the experiment, that will give us a strong support that fractionalization do occur in the system. Right? So the idea is, this is just the idea. So we use a weak magnetic field. The field cannot be large. If the field is large, the spin gets fully polarized. So you destroy the state. You destroy the spin liquid state. Imagine the spin liquid was there originally. Now you apply strong field, the spin gets all polarized. So the state is gone completely. So what we keep the state in there, is keep the state there with the weak field. The weak field just do something little to the system. So because spin liquid is robust against the small weak perturbation, you apply something weak. Yeah. So then you can make prediction. The spin-on remains to be the description of the magnetic situation. So this is a prediction we made with my student. Originally the spin-on bands are degenerate up and down degenerate. Now you apply Zeeman coupling. So this is you get quite a stability between these spin-up and spin-down bands. So then the excitation can be predicted. So this is a theoretical prediction. So you create a diamond shape or cross-shape at the gamma point. Originally it's this thing. Originally without field it's this thing. We just step. Now become this clocking thing. And the continuum remains, we still have this shape. So this is a theoretical result performed by my student and I. And this is the experiment. This is the experiment.
So where do you add the weak field?
This is the simplest theory we said.
So where do you add the weak field to the phenomenological model or to the microscopic model?
To the phenomenological model.
To the Fermion with the chemical.
Yeah.